Hi, in this lesson, I want to talk a bit about the shapes that we can see within minerals. Now, these can be formed in a couple of different ways, um, either by the shape of the crystals themselves or how they break. Either way, they can be quite distinctive for particular minerals. So let's have a look at what they are. Now, crystals can grow in a number of different, very distinctive shapes. All these shapes I'm going to show you are actually all natural. This is the first. This is cubic crystals for fairly obvious reasons. This is actually pyrite or fool's gold, which, if it can grow without sort of being restricted in any way, will grow these almost perfect cubic shapes. It's really distinctive. It's not the only mineral to grow in this shape. Um, Galena and halite, which are two other ones we need to know on our list, will also form this distinctive pattern. The second of these is what we call a rhombic crystal. This is where all the crystal faces are rhombuses. Uh, the angle between each of these crystal faces is 60 degrees, and it's very distinctive of one of the minerals we need to know called calcite. Some minerals like this quartz can grow into these hexagonal columns. Um, Again, it can be a very distinctive shape, particularly where these columns then, as they do in quartz, come to that pointed prismatic top. This is quite an unusual one. This is what we call a mammillated or reniform shape. And what we see here, these sort of round, they almost look like bubbles on the mineral surface. But those are actually solid mineral. A mineral called hematite on our list is one that forms this type of distinctive habit. We can also get minerals that are foliated. Foliated means sort of leaf-like. So we get these parallel sheets that grow within the mineral. This is extremely distinctive stuff. Mica is the mineral we need to know that demonstrates this. We can also get minerals that just grow in columns. These can be four-sided, six-sided, possibly even more. Augite, for example, will grow in a columnar form. Let me show you now what this looks like in minerals. These are some of the different crystal forms, or habit is another word that we give them. You can see from this collection that there's a whole series of very distinctive shapes of crystals. Some of these are bladed, others form columns, like this mineral of kyanite. These distinctive shapes are a feature of the way the mineral is put together, how the different elements within the mineral actually fit together in its crystal lattice. There are several of these that we can fairly easily recognize. We have cubic minerals, like this crystal of pyrite. It looks like it's been made, but this is a completely natural shape in the way it's grown. That could be in a slightly different form, like this crystal of a mineral called fluorite. Still though with the square shape. This is calcite, a very distinctive rhombus shape crystal. Quartz has a distinctively hexagonal shaped crystal. This is when it can grow as a crystal. The 6 sides of the crystal then each come to a point at the top. It's create like a prism that we see. Some minerals, this is augite, create these columns. There are even some unusual crystal forms. This is a mineral called mica that creates what we call a foliated pattern, like these flexible sheets. So we can see that where crystals get a chance to grow, they can form some distinctive shapes. These can be helpful in identifying these minerals. The second way minerals may be shaped is how they break apart. And where we see a regular pattern of minerals breaking apart, it's because there's a weakness in the way the elements are put together within the mineral. This can be really distinctive. So we can have minerals that have a cubic cleavage that will break apart in 3 different directions, each of which will form a flat, regular surface in the mineral. Now, those 3 minerals, or those 3 surfaces, are all at 90 degrees. If they're not at 90 degrees, like in this case, where the mineral surfaces, the cleavage planes, are at 60 degrees to each other, this will create what we call a rhombohedral cleavage, because it creates rhombus shapes within the mineral. We can also get what we call basal cleavage. This is where there's one parallel plane of weakness running through the mineral, so the mineral will always split into these parallel sheets. Now, these cleavage planes, these surfaces that break, can be described as being good if they're really flat and really regular, or poor if they're a bit rough and a bit they're not completely flat. You will see these descriptions in your mineral data sheet. Let me show you how this works. Cleavage is the way a mineral will break. This can be one of the trickier properties to recognise, but with a bit of practice and a bit of careful observation, it can be very, very useful. Minerals can have distinctive cleavages because of the way the elements are put together. If there are weaknesses, flat surface of weaknesses within the crystal, then that's the way the mineral will break most of the time. For example, this is a crystal of mica. Now, mica has what we call a basal cleavage, which is one plane. You can see that there are sheets within the mineral running parallel to my hand there. If I try and break this mineral, it will break in sheets that are all parallel to each other. So we can see how this mineral is coming apart to create these thin, flexible sheets. It looks fake, but this is completely natural. That's one plane of cleavage, a basal cleavage. We can see minerals that have 3 planes of cleavage. This is an example. This is galena. And if we look carefully at this face of galena, you can see that the way this crystal is broken creates a whole series of different cube shapes. So we have 3 planes of cleavage here, 3 directions in which it will break: this way, and this way, all at 90 degrees to each other. Now there are some minerals that have these three planes of cleavage that aren't at 90 degrees to each other. This is an example. This is calcite. Now calcite also has three planes of cleavage. You can see that we've got one there, we have one on that surface, we have another one on this surface. And you can actually see the cracks running through this mineral parallel to those surfaces. But these surfaces aren't at 90 degrees to each other. They're at about 60 degrees to each other. And what we see as a result is a rhombus shape. You can see it quite clearly in this part of the crystal here. That's very distinctive of calcite. Now sometimes there are minerals that have maybe only two planes of cleavage. This mineral here is a type of feldspar. And you can see here that there are two planes of cleavage. We get flat surfaces running at 90 degrees to each other to create this shape here. But where we'd expect to see a third plane, it doesn't break that evenly at all. It's not a flat surface. So this particular sample only has two planes of cleavage at 90 degrees to each other. Again, that's quite distinctive. So cleavage can be a very important property to identify a mineral. Okay. The final thing we need to look at is if there aren't any weaknesses. And this creates a feature when we try and break a mineral called a fracture, which could be uneven, hackly, or conchoidal. Let me show you how they work. Sometimes minerals don't have weaknesses. They're uniformly strong all the way through. Where this happens, when minerals break, it creates a feature we call fracture. Now, fracture isn't as useful as cleavage. But if we look at these minerals, you can see here, this is rose quartz, and you can see there's no real pattern at all to how this crystal was broken. This is what we call an uneven fracture. This sample though, this is agate, you can see has some curved patterns. It's not the best sample to show this, but it's not too bad. Those curved patterns on the surface are what we call a conchoidal fracture, which means shell-like. Some quite hard minerals can demonstrate this property. The Hackley fracture you can see in your booklet. I'm afraid I don't have an example of that. It's quite an unusual one. Okay, so to conclude, these distinctive shapes that we can find within minerals can be really useful in helping us to identify them. Crystal form, if we get some nice well-grown crystals, or cleavage, which for some minerals is really distinctive, can be very helpful for us. But these aren't the only properties. We need to think a little bit more about some of the other properties that will help us identify minerals. More of that next lesson.